In this video, we're going to look at using the first derivative test to find local extrema, and we are going to then apply that to motion. And then we're going to look at using the second derivative to determine the concavity of a function, using the first and second derivative graphs to figure out things about the actual function, finding inflection points, and then we're going to talk about using the second derivative test. So first, the first derivative test is where you find those critical numbers and you figure out where you have a change from increasing to decreasing based on those critical numbers, or decreasing to increasing. That will tell you if you have a local min or local max. Remember that we use a sign chart to determine that, but when you are justifying, you cannot use a sign chart. You have to explain that there's a change from negative to positive in this first derivative, or positive to negative, to justify why you have a max or a min. So here, to find the local extrema, we're going to take the derivative. And so here we get the derivative is 4x to the third minus 12x squared. Take out a 4x squared, and we're left with x minus 3. So we have critical numbers at x equals 0 and x equals 3. Make our sign chart. And if our number is less than 0, this piece is going to be positive and this piece is going to be negative. So that gives us a negative. If we're between 0 and 3, this first piece will be positive again. This piece will be negative. So we have a negative once again. And if x is greater than 3, both pieces will be positive, and so we have a positive. So we know that because that f of x is increasing, on the interval 0 to 3, since the derivative is positive. We know that f of x is decreasing on the interval negative infinity to 0. Oops, sorry, this should be to infinity. So this is negative infinity to 0 and 0 to 3, since the derivative is negative. That tells us that there's a sign change from negative to positive, and therefore we have a min at x equals 3. On this one, our derivative, I'm going to go ahead and multiply that through and get x to the 5/3 minus 5x to the 2/3. So the derivative, this is f of x. So the derivative is going to be 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. That's 5x to the 2/3 over 3 minus 10 over 3x to the 1/3. So if we get a common denominator of 3x to the 1/3, we have to multiply this numerator by x to the 1/3. That just gives us x, and minus 10 for the other part. So then 5x minus 10 equals 0 when x is 2, and then when x equals 0, the derivative is undefined. So there's our two critical numbers. If x is less than 0, the top and the bottom are both negative, so then this becomes positive. For between 0 and 2, the top is going to be negative, the bottom is going to be positive, so that gives us a negative. And if we're greater than 2, they're both positive, so that gives us a positive. So that tells us we are increasing from negative infinity to 0 and 2 to infinity. And decreasing from 0 to 2. That means that we have a min where we change from decreasing to increasing at x equals 2, and a max where we change from increasing to decreasing at x equals 0. When we have a graph, to determine the critical numbers, we're just looking for where the derivative is undefined, which doesn't happen on this graph, or where the derivative is equal to 0, and that happens at x equals 0 and x equals 2 in this graph. The function is going to be increasing where the derivative is equal or is positive, and that happens from 2 to infinity. Decreasing is going to be where the derivative is negative, and that happens from negative infinity to 0 and 0 to 2. We have a local min when the derivative changes from decreasing to increasing, and so that happens at 2. We have a local max where the derivative changes from increasing to decreasing, and that doesn't happen here, so there are no local max values in F. For motion, we know that the velocity is the derivative of the position function. And so if the velocity is positive, our function is moving to the right. If the velocity is negative, our object is moving to the left. And if it is 0, we are moving to, or we're at rest. We're not moving at all. So here, v, the velocity, is going to be 3t squared minus 18t plus 15, and that factors 3t minus 5, t minus 1. So that tells us that there are critical numbers at 5 and 1. And we know that the time has to start at 0. So between 0 and 1, we're going to have a negative and a negative, so that gives us positive there. Between 1 and 5, we have positive for one piece but negative for the other, and greater than 5, they are both positive. So looking at that, that tells us that we're going to be moving to the right when we are positive, and that's between 0 and 1, and then 5 to infinity. We are going to be moving to the left where it's negative, and that happens between 1 and 5. We reverse direction when we change from the positive to the negative, so that happens when the time is 1. And then for the velocity increasing or decreasing, we are going to take the derivative to get the acceleration. The derivative of the velocity function is just 6t minus 18, which factors to t minus 3. And so for acceleration between 0 and 3, we have negative, and bigger than 3, we have a positive. So we are going to be, the velocity is increasing at 3 to infinity and decreasing between 0 and 3. For concavity, you take the second derivative. If the second derivative is positive, we have concave up. If the second derivative is negative, we have concave down. So here, when I take the first derivative of e to the x, I get e to the x. Second derivative of e to the x is also e to the x. E to the x is always positive, and therefore always concave up. On this one, if we want to find the local extrema, the first thing that we're going to do is take the first derivative, and that is 3x squared minus 12x plus 9. So x minus 3, x minus 1. So we have critical numbers at x equals 1, x equals 3. And we have negative, negative, which gives us a positive, negative, positive, positive, positive. So then we know we have a min at x equals 3, max at x equals 1. And again, to justify those, if it said that we had to justify it, we'd have to explain that we had that sign change, or that change from increasing to decreasing at 1, decreasing to increasing at 3. For part B, we want to know concave up, concave down, so we're going to take the second derivative. The second derivative, 6x minus 12. So we have a possible point of inflection there at 2. Before 2, we have negative. After 2, positive. So we are concave down from negative infinity to 2, concave up from 2 to infinity. So I talked about that idea of an inflection point. An inflection point is where there's a sign change with the second derivative. So you want to find where the second derivative equals 0 or doesn't exist, and then if there's a sign change on either side of that, that is an inflection point. So unlike critical numbers, remember, inflection points have to have a sign change. Extrema have to have a sign change. Critical numbers do not. So if we're going to find the inflection points for x to the 5/3, first find the first derivative, and then find the second derivative. So does not exist at x equals 0, and it's going to be negative when x is before 0 and positive after, so we have a point of inflection at x equals 0. Okay, in this example, we are going to be using the first derivative and the second derivative to answer these questions. So if we want critical numbers for the function, we're going to look at the first derivative. Remember, critical numbers are simply where the first derivative is undefined or 0. That happens at x equals 0 in this graph here, and at x equals 4/3. Increasing where the derivative is positive, and so that happens between negative infinity and 0, and then that also happens between 4/3 and infinity. Decreasing where the derivative is negative, so that happens between 0 and 4/3. We would have a local min when we change from decreasing to increasing, so that happens at x equals 4/3. A local max is going to happen when we change from increasing to decreasing, and that happens at x equals 0. For concave up and concave down, we're going to look at the second derivative where it's undefined, or where it's positive for concave up, and that happens from 1 to infinity, and where it's negative for concave down, and that happens from negative infinity to 0, and then also from 0 to 1. Inflection points only happen where you have a sign change, so there's no inflection point at 0, but there is an inflection point at x equals 1. And finally, the second derivative test is never necessary. You can always use the first derivative test, but you might be asked on the AP to use the second derivative test in a free response question. So the idea is you find those places where you have critical numbers, and then you test those x values in the second derivative. And if the second derivative is negative, that means that you have a maximum value. And if the second derivative is positive, then that means that you have a minimum value, and that has to do with concavity. If the second derivative is negative, your concave down makes a max. Second derivative is positive, your concave up, that makes a min.